This is Jim Hendershot, and this next lecture is lecture number 15, and this is one of the most important topics for designing machines. It involves the stator phase circuits and coil designs and coil placements. As we progress along in the design of a machine, at some point you've selected whether you're going to use a wire delta connection or whether you're going to use series or parallel connections inside those Y and delta connections to adjust your number of turns. Let me point out that with permanent magnet machines, delta phase connections are very dangerous unless you're able to guarantee balanced phase windings. Otherwise you get circulating currents in the delta. I don't think I've mentioned that before. It's important to mention that. So what you need to do, whichever one of these wire delta connections you pick and slot and pole numbers, you've got to select where the coil locations are, whether they're full pitch or short pitch, so that you get the highest winding distribution factor. And then you select the number of turns based on the required ampere turns and voltage for induction machines and reluctant synchronous, and based upon the voltage constant required for surface mount and internally permanent magnet machines. The number of turns per coil is based on the back EMF voltage, to make sure that's lower than what the DC supply voltage is at the max speed you're going to produce power. So you select the initial wire gauge for about 40% slot fill. We've talked about that before for either single layer or multiple layer winding. Okay, you can calculate the coil resistance from the mean turn length times the number of turns times the wire resistance per meter. Now, strands in hand of a smaller gauge. If the gauge is fat, then use multiple strands in hand. That makes wire insertion more flexible. Litch wire may be required for high frequency machines. We've already discussed that. Determine the end turn configuration that has to be formed and laced and sometimes even supported to be against vibration in real big machines where the mass of the end turns are huge. And your terminations and egress to the wire egress, lead egress, depends on whether you use magnet pigtails right out to terminal studs or whether you attach lead wires to the pigtails and bring lead wires out for connection to the inverter. And then VIP or encapsulating the stator to retain the conductors from vibrating, improve thermal conductivity. And as we said, large machine require end turn support against vibration. And for insulation topics and details about how to insulate the windings, see lecture 13. The current imbalance in parallel phase conductors is a big problem, and time-varying currents introduce magnetic fields that redistribute the current density in the conductors, and the most troublesome effects of this are above 1 kilohertz. This is known as skin effect losses and proximity effect losses. If the current doesn't distribute itself equally in all parallel paths, you're going to experience a higher impedance at frequency in operating than your DC resistance. We've talked about these before. Even the location of the conductors within the slot changes the inductance. For example, conductors in the top of the slot close to the slot opening have lower inductance than the ones in the bottom of the slot because they have more iron around them. So normal lap coils, you'd have a coil, half of the coil, one side of the coil would be in the top of the slot, the other side of the coil would be in the bottom of the slot. But so that balances out the induction situation very nicely. But if these are parallel strands for one turn, you can get variation in inductance from each of these strands, from this one to this one. So sometimes you have to use litch wire or use some transposing of these coils. This is what skin effect is all about. It seems that at high frequencies there's a skin depth here, and the current tends to concentrate. The current density is highest around the outside. So the way to do that, the way to solve that problem, use litch wire, which consists of a bunch of strands. Here's a bunch of and the cross section of this, each one of these equals, there's a solid wire. So there's a solid wire. So the cross section of all these little strands has to equal the cross section of a single conductor you've designed it to. But the more strands you have, the closer the skin cross-sectional area for each strand added together equals the cross-section you need. It has to be used with limitations. It doesn't take care of proximity effects always. It depends if every strand is transposed through the length of the core, then it does the same thing as a robo winding, which is a transformation method. Details of this practice are left to creative designers. Proximity effect is looks like this. It's where you have high current density concentrates on one side of the machine. Here's an actual slot that's been modeled by finite element method. This is close to the air gap, and you see where the current concentrates on the sides of the conductors closest to the air gap. Way deep in a slot, there's very low current density out there at all. So this will give you a high impedance. This is what a transposed rectangular wire coil looks like. As you can see, let's say that this from here to this part of this phase winding is the part that goes down the slots. So the core ends right here. We're not showing the end winding to connect this to the other sides, but this is how these are all parallel strands for the same turn, and you want the current to flow equally in all of these. So to get it to do that, because the proximity effect and the difference in inductance from the bottom of the slot to the top of the slot, you transpose each one of these conductors back and forth. So every one of these occupies every position in the slot. There's a way to do that if you have random wound coils. Here's an example of that. If you can follow this, this is a 4-pole motor with 24 slots, so that we let's say however many turns we need per coil, we use groups of wires in hand to achieve the cross section that we need. And we break that up, say since there's 4 slots per pole per phase, with this situation, you break this up into turn that crazy phone off. You break the conductors up, the parallel conductors up into 4 groups. And you divide the slot depth into 4 sections, 1, 2, 3, 4. They're color coded here. So you put on the first coil, you put group 1 in position 1. In the second coil, you put the position group 1 in position 4, and then in position 3, and then position 2. Or I should have gone the other way. Group 1, 2, 3, and 4. So all these groups occupy every position, because instead of transposing them in the slot, you transpose the coils that are connected in series into different slot locations into the four slots that carry these 4 coils. So that way you've transposed them, and you have the same proximity exposure and inductance exposure for every phase. They're exactly the same, because you've divided up in groups and transposed them by slots rather than in the same slot. The winding distribution factors versus poles. Unity means that the center of the winding is over the center of the poles. That's a good thing. A full pitch winding usually means, if it's an integral slot winding, because the number of poles divides evenly into the number of slots, that's an integral slot winding. So that means that if a full pitch winding is going to give you a winding factor, a distribution factor of 1. Once the pole and slot number have been selected, you select the slots for coils per phase. See Lecture 10 for that, for determination of the combination of balanced slot and pole combinations. There are very little published papers or articles on this topic. I think I've published as many as anyone. Some configurations, such as integral slot windings, are somewhat obvious, or you can copy them from other motors. You know, like a 4-pole, 12-slot stator. The coil location for that is pretty simple, pretty obvious, and multiples of that, 8-pole, 24 slots. All those are pretty obvious as well. Full pitch, short pitch winding, those are pretty obvious. But the fractional slot combinations are tough to figure out, and you almost suspect that companies keep trade secrets. They're all definable by the principles and formulas set out in a famous book by a German by the name of Lucius Gehrig. I mentioned that before, and the patent office even awards patents on slot and pole combinations, winding combinations that are really covered by the formulas and principles in Lucius Gehrig's book. But I guess the patent examiners don't know that that book exists. But anyway, at any rate, some of these fractional slot combinations have a multitude of winding patterns. For example, this 12 slot stator and 10-pole rotor for 3 phases has 6 different winding patterns possible for balanced 3-phase windings. Only one of them has a very high winding distribution factor, and so how do you find that one? And that's the one you should use. How do we come up with these winding patterns? Well, one process here that's quite popular in Europe, it's promoted by Professor Reichert from Switzerland, and it's been taught around the world by many professors, including my friend Professor Valerie Habrakova of the University of Zilina in the Slovak Republic. I'm really indebted to her work and what she has taught me about how to understand this technique, and I'm certainly pleased to pass along this lecture, include it in this lecture, because there's very little published on this important topic. And this method is based on the fundamental principles of rotating magnetic fields inside the stator, but we think of that as that rotating field rotating inside the air gap in a cylinder between the rotor and the stator. So this example here is a 2-pole rotor, and there's 3 sinusoidal distributed windings in this stator, and they have to be physically located 120 degrees apart. And here we see a plot of the 3 sinusoidal currents 120 degrees apart that the inverter's got to supply to this machine, and the rotor will see these 3 sinusoidal currents and linked with the rotor flux, providing that we've got the coils placed in a balanced fashion 120 degrees apart. So that's given any number of coils, we got to figure out how to do that. Well, the pole and phase winding, they have to be linked like the diagram in the previous slide, so we can determine the coil location. I just said that. So we have to start with some definition of terms used to express the relationship used to determine the coil placement, so we can make some calculations. So M is the number of phases, capital Q is the number of stator slots, 2p is the number of phases, with this little p being the number of pole pairs, so twice that many is the total number of poles. And this angle here is the pole pitch, where D is the stator ID, or the rotor OD is close enough, and of course we got the number of poles in the denominator. We got pi up here. So Q sub P is the number of stator slots per pole, which equals the total number of slots, obviously, divided by the number of poles. Where that equals Y, as long as Y is the span of each coil. If Y equals the angle between the stator slots per pole, then the span is full pitch and is identical to the pole pitch. So if we consider the number of slots per the number of phase, and by the way, this must be an integer. For balanced windings, you're going to use all the slots, and that means that the number of phases have to divide into the number of stator slots evenly with no remainder. The number, now if I take then the number of stator slots and divide it by the number of poles and the number of phases, divide the number, so I wind up with the number of slots per pole per phase. Now this could be an integer or a fraction. If it's an integer, it's considered a integral slot winding. If there's a remainder, it's a fraction, and it's a fractional slot winding, and those are the tough ones to do. So n is the number of turns in series per phase, and 2n is the number of conductors per phase. That's Z. Z is the number of conductors per phase times the number of coils per phase. That would be Z per phase. So the number of conductors in one slot equals this term. Using these relationships, we can create a winding phasor diagram and determine the phase coil locations. So what do we need to do? Well, first we got to have a phasor diagram along with a stator cross section with the slots numbered so that we can find out where the coils go. And then we can create a slot list for the coil placements for each phase. The linear winding diagram, or the pattern, if you lay out the slots in linear fashion, as you've seen on a lot of documentation, then you could find out where all the coils go from this data. So here's, on the left here, here's our stator cross section showing the 12 slots, and this is a 2-pole machine. So it's poles equals 2, phases equals 3, cross section on the left with a stator phasor diagram on the right. Phases 3, number of slots 13, so what you have is you need a phasor for every slot. So we got 12 slots, so 12 into 360 degrees means the adjacent slots are 30 degrees apart. That's important. Okay, so from that we can determine the resulting phase voltage diagrams spaced 120 degrees apart, and these are the slot locations derived from this this diagram here of the phasor diagram. So from that diagram that you can determine this is the linear layout of the slots is one way to do it, and from that diagram you can come up with 2 possible ways to insert the coils. The one on the left is a lap winding where the coil span's the same. You see here this is a 6-slot span. The second coil is a 6-slot span. And the right is a concentric winding where you still have 2 coils, you still have the same number of conductors linking the magnet flux. That didn't change at all, but the only difference is how they're connected in the end terms. This pattern here can be machine inserted, because you could put a smaller coil inside the larger coil, and the finish of the smaller coils is of course connected to the start of the larger coil, or vice versa, so that you can insert both of these coils at once with automatic insertion equipment, because the one coil is inside the other, and the resistance per phase is no different. This is a little longer, that one's a little shorter, because this one's a span of 7, this over here it's a span of 6, so that makes the end turns longer by some amount. But instead of the other coil being a span of 6, it's a span of 5, so the increase in end turn resistance here is compensated for the decrease in that one, so they come out the same. So from this data, if you lay all the coils in here from the previous graph, then you can make a slot list from 2 or up down or down up list for where all the coils go. Now this is Reichert and Steinbrink. They show the phasor diagram like this, which is very interesting and kind of helpful to show you how to do this. In that you see what we have here are our 120 degree phase vectors where we're going to apply the current. And then you have a phasor diagram here of a phasor for every one of the coils. So if we see, we have 12 slots and 10 poles. So if we determine what the angle is between slot number 1 and slot number 2, we do that. This angle shows us how to number these slots, so you can come up with your winding pattern. So this angle is 360 degrees times the number of poles divided by the number of phases. And so you have 360 divided by, or multiplied times 5 divided by 12 gives you 150 degrees. So each one of these is 30 degrees apart. So 30 degrees into 150 is 5. So you count 1, 2, 3, 4, 5 of these slots. So that's why you number this slot number 2. So looking over here, here's slot number 1, there's slot number 2. Okay? So that means that we have to wind the first coil from slot 1 to slot 2. It goes across that tooth there. All right, now how do we find the first coil location for phase B? You count 5 again. 1, 2, 3, 4, 5, 150 degrees. 1, 2, 3, 4, 5. So here is where you number slot 3. 1, 2, 3, 4, 5. Now that's how you number slot 4 that we're going to see over here. Count 1, 2, 3, 4, 5. Here's slot, the first slot, which is slot 5. That's the first slot where phase C goes. And so on. You keep going around till you have all these slots numbered. And remember, we've color-coded here phase A, phase B, and phase C, or maybe it's A, B, and C. So you color-code them here. So now from this slot numbering, you could pick where all the coils go and develop your winding chart by calculating this angle, which is a relationship between the number of poles and the number of slots to determine where all the coils go. That's a neat system. Here's a plot of these coils along the voltage star, right along the three vectors where you're going to apply the current. Remember, you're going to apply current in here. And it's going to go through all these coils. You're going to apply current there. It's going to go all three coils. And that's how that ties in with this diagram here. So this works for most any motor. It gets a little tedious, but this is a graphical way of determining all your winding coil locations. So that concludes this lecture. Thank you very much.